I've had many students over the years say, I've heard of the Monte Carlo method, but I'm not sure exactly what it is or what its usefulness is. This lecture goes over the background and central idea of Monte Carlo analysis to give you a better understanding of its potential uses in science and engineering. The items we'll cover today are the history of the Monte Carlo approach, what is Monte Carlo analysis and why it's useful, and we'll also give a few illustrative examples. Monte Carlo is actually a code word invented during the Manhattan Project. It was discovered and formalized by two physicists, Ulam and von Neumann. This is a picture on the right of Ulam. He's at the Institute for Advanced Study in Princeton there. Ulam was recovering from an illness, so he was in bed by himself playing solitaire, and he came up with the following idea, that in many probabilistic phenomena, especially those with complex interactions or complex games of chance, like the outcomes of a card game or solitaire, you can obtain the probability density just by observing many, many trials over time. Now, at the same time, the first computers like the ENIAC were being developed, so he asked, why not observe many trials of some complex system via numerical simulation? The key idea behind Monte Carlo analysis is that if you know something about the underlying physics of some phenomenon and how it interacts with other phenomena, let's say a subsystem interaction within a larger system, then you can determine a probabilistic description of the total system behavior using Monte Carlo. Next, I'm going to talk about a process that Ulam and von Neumann were presumably thinking about during the Manhattan Project. To do that, I'm going to describe some nuclear physics, but don't worry, this is just to introduce some of the terms. In the element uranium-235-92, which is shown here, 92 is the number of protons in the atom, and 235 is the number of total nucleons, which is protons plus neutrons. So on the left, you see a neutron that's being absorbed by a uranium-235 atom. That becomes uranium-236, which is fissile, and that's why I have the asterisk there. When uranium-236 atom fissions, it creates two byproduct atoms, one isotope of iodine and another of yttrium, in addition to two neutrons and heat Q. Now, the iodine-137 isotope is unstable, and it gets converted to a xenon isotope through what's called beta decay, which means that it loses an electron. Xenon-137 is also unstable, and through neutron emission, it converts to xenon-136. Note that there are other fission byproducts that are possible here. This is just showing one possibility. In the initial reaction at the top that produces two neutrons, that's called a prompt reaction, whereas the neutron emission from the xenon is a delayed reaction. Those neutrons can further be absorbed by other 235 uraniums. The total heat that's released in this chain reaction can either happen very quickly in a destructive manner, or if you space out the energy release over a long period of time, that's useful in power plant applications. We'd like to model this process in order to figure out certain design parameters. What I'm showing here is a cross-section of a piece of uranium. It contains 235 and 238 isotopes. Raw uranium is less than 1% 235, and with the rest being mostly 238. However, the 238 only becomes fissile if the absorbing neutron is very high energy. In this simple example, the length of the material is capital L, and the distance between the atoms is denoted delta. Suppose we have a neutron that gets absorbed by the 235 isotope. In order for it to get absorbed, first of all, the neutron has to have enough energy, and secondly, it has to be within the nuclear radius, which is only about a femtometer, and then it gets absorbed with some probability. But let's say that it does, and the 235 isotope becomes the 236 isotope, which again is fissile. Sometime later, the 236 isotope splits into two byproducts, releasing heat, gives off two prompt neutrons, and then later on, remember the decay released another neutron. What I'm showing here is one of the prompt neutrons, and with some probability, this neutron will reach this other 235 uranium isotope inside the material. Note that in order for this neutron to impinge upon another 235 isotope, it's dependent upon the ratio of the 235 to 238 isotopes within the material, i.e. the purity. Let's say that this neutron gets absorbed, becomes the 236 isotope, which is excited. Let's say that that splits into two byproducts, releasing heat, and here's another prompt neutron, which hits this 235 isotope in the right with some angle. This becomes excited, and then finally it ejects another neutron again, releasing heat Q sub 3. What I'm showing here is a 2D view, but in reality, this is a 3D structure. One of the practical design questions, if you're evaluating a reactor design, is what is the neutron flux that's exiting the material here? If we wanted to know the average neutron flux exiting the material at some point on the outside of the material, the neutron flux measured in neutrons per centimeter squared per second may look something like this. What I want to know here is what is the probability distribution of the neutron flux and what is its mean, here denoted sigma bar. In the simple model that I showed earlier, you can see how in principle you could calculate the neutron flux. However, there are a lot of built-in probabilities that make the analysis difficult. To give you an example, some of the random variables in the previous process were the absorption of neutrons by fissile elements, the uranium-235, whether a neutron actually gets absorbed, the time of fission itself, in addition to which way the neutrons scatter. Most of these probabilities are actually based on quantum mechanics. It would be very difficult to compute average neutron flux based on all the joint probabilities. However, Monte Carlo analysis can be used and is used to do these sorts of calculations. Here's a working definition of Monte Carlo analysis. It's a method of numerically synthesizing statistical behavior of complex stochastic systems. Hopefully that last example illustrated how Monte Carlo analysis could be useful. I'm going to now compare Monte Carlo analysis to purely analytical methods and a few problems that are more tractable to really demonstrate its usefulness.